4.1 presentation on gas laws. It says pressure pushing down on me, pressure pushing down on you, no man can ask for. It's a famous song by David Bowie. So, it's called Under Pressure. So, the learning goals for this presentation are number one, that you be able to evaluate the assumptions of KMT and how it relates to gas laws, that you be able to calculate an unknown for both ideal and real gases, and that you be able to relate gas laws to stoichiometry. So the first thing we need to look at is kinetic molecular theory. Kinetic molecular theory is a theory that describes the behavior of what we call ideal gases. Now, ideal gases are a model based on a number of assumptions. Now, the kinetic molecular theory works whenever you have the assumption that it is at a high temperature and that the pressure is relatively low. Now, whenever those assumptions are thrown out the window, then KMT doesn't always work. But let's look at the individual assumptions. The first assumption of KMT is that gases are very, very small molecules. In other words, that these molecules take up negligible volume compared to the container. So if you were to look at it, here's one atom of gas, or one molecule of gas, and this is a negligible volume when you compare it to the entire container. So that's an assumption number one. It explains why the density of gases is irrelevant. It makes no sense to talk about the density of a gas because the volume of a container is mostly empty space. So it's really hard to say what the density of a gas is in a container and have it actually mean anything. KMT assumption number two is that molecules are in constant random motion. Whenever you're in constant random motion, that allows you to use some statistical tools, something called the Boltzman Distribution for large numbers, and you can kind of get an average of all the molecules that are in a particular sample. Number three is that the collisions are numerous. Okay, you're going to have a lot of collisions bouncing off and forth between these molecules. They're going to collide often, and that each one of these collisions is going to be an elastic collision. Now, an elastic collision means that whenever they hit together, they're going to bounce off with the same amount of kinetic energy that they had before. In other words, kinetic energy is conserved. So if this comes in with 10 meters per second, this is going to bounce off with 10 meters per second. Okay, before and after the collision. So the kinetic energy is going to be conserved. Now, it doesn't always have to mean the same velocity, but it does mean you have to have the same kinetic energy. And remember, kinetic energy is 1/2 mass velocity squared. So basically what it's saying is there's no real loss of velocity when particles collide. The fourth assumption is that there are no intermolecular forces between molecules. Now, the reason why you have this right here, this assumption, is saying that molecules are far enough apart that whenever you have a partial positive charge and a partial negative charge for gases, that they're so far apart that this attraction between the two won't actually have any sort of real effect. Kinetic molecular theory assumption number 5 says that the kinetic energy of a molecule depends on the temperature. That's something we've talked about before, that as you increase the temperature, you increase the kinetic energy. And that's the formula we have, Ke equals 3/2 kT. So these are the 5 assumptions that you have of kinetic molecular theory. Now, the one thing we need to go into a little bit more detail on is what's called the Boltzman distribution. The Boltzman distribution is not just for atoms, it's actually a probability, it's a statistical function that allows you to look at the average of a whole system. So what we call it is it's a probability distribution. Now, in this particular case, it's a probability distribution of velocities when you have a certain amount of temperature. So this right here is telling you the number of molecules that are at that particular speed. These right here are the temperatures that you have. Now, this is obviously in the Celsius scale because you couldn't have a negative 100 Kelvin. That wouldn't work. So whenever we say negative 100 degrees Celsius, what that means is this right here is my distribution. So I do have some that go past 600, but my peak right here is this average is somewhere right around the 300 range. Okay, about 300. As you increase the temperature, and we'll just use a different color. As you increase the temperature to 600 degrees Celsius, you notice how it's a flatter curve. It's a flatter curve because there are more possibilities for the molecules to be. So you're not going to have a big peak like you are whenever you have a more confined temperature range. Okay, but if you look right here, the middle point of this is somewhere on the eyes of 700, 750 right there. So a higher temperature widens the possible velocities, and you don't get as many. You don't get a giant peak. Instead, you get a wider, flatter curve. Pressure. Okay, pressure Gas pressure is the force exerted is the force a gas exerts over the surface area of the container. So if you were to look at it, it actually gets to be very difficult to calculate the surface area of a container because a lot of the times we're working with things like volumetric flasks and things like that. It doesn't really work that well. But it is generally kind of easy to do it for a beaker. A beaker is basically a cylinder without the top. And so you can do that relatively easy. Now, pressure equals force over area. We do have lots of units for pressure that we've talked about. Generally speaking, force is measured in newtons, and area is generally measured in meters squared. Now, if you were to use these particular units right here, the newton and the meter squared, you would get pressures in a unit called a pascal. Now, a pascal is a relatively small unit of pressure, so we tend to not use things like pascals. Instead, we look at other units, and the other units that we look at more commonly are the kilopascal, and the kilopascal is really particularly useful whenever we're working with liters. Okay, if we want to go into standard units and we want to use liters, the kilopascal is great. Okay, another common unit that we use is the atmosphere. Okay, the atmosphere is really useful when we look at the ideal gas law constant, which is an R value, and it has units of 0.00821 liter atmospheres per mole Kelvin. So whenever we use that, we want to have our pressure in atmospheres. So although the pascal is the standard unit of pressure, really these two are much, much more common. An example of that is you see this here. It says, a student is investigating the pressure in a balloon, that a certain balloon will pop under 5 atmospheres of pressure. What force can the student press down on the balloon with without popping? There are 50 nails each with a surface area of 1.8 times 10 to the minus 12 meters squared. So you notice this is a really small area, which makes sense because a nail has a relatively small surface area. The first thing I want to do is I want to identify what I'm trying to find. And it says the student is trying to, what force, so I'm trying to look for the force. Okay, I know the equation that I'm going to use is pressure equals force over area. I know that I have my area here as 1.8 times 10 to the minus 12th, but that represents the area of a single nail. I have to multiply it by 50 in order to get the overall area. And the overall area ends up being something like 9 times 10 to the minus 11th meters squared. Okay, the next thing that you'll notice is that's our area. You also have the pressure. The pressure that it gives you is 5 atmospheres of pressure. Okay, you generally can't use 5 atmospheres of pressure because it's not in a unit that makes any sense. Remember, generally speaking, when I'm using this equation right here and I'm trying to use it in standard units, I have to convert this thing from atmospheres to pascals, 101,325. When you multiply that out, the standard units of the pressure in this case is going to be about 506,625 pascals. At that point, you have your two numbers that you can then use and plug into the equation. So it's a 506,625 equals the force divided by the area, which is 9 times 10 to the 11th. Multiply it out, you end up with a very, very small value of the force, which is about 4.56 times 10 to the minus 5th newtons. Okay, the next example says, or the next thing we need to talk about is Dalton's law of partial pressure. Now, Dalton's law of partial pressure is a way of saying that pressure is an additive thing. If you think of pressure as the force of each collision divided by the area of the container, well, if you add another gas in there, what you're going to do is you're going to add to the pressure that's there. You're going to have the pressure of each one added together gives you the total pressure there. So the total pressure is equal to the pressure of each individual gas. Now, if you have 3 gases, it stops at P1 plus P2 plus P3. If you have 2 gases, it's P1 plus P2. If you have an infinite number of gases, it goes all the way to P infinite. Okay, so those are one of the things you look at for Dalton's law of partial pressure, is that the pressures add to be combined together. An example of this says, a student is attempting to quantify the amount of hydrogen created in a chemical reaction by determining the pressure. Hydrogen is highly flammable, so the student mixes it with 1.4 atmospheres of inert argon gas. It's a way of being able to render the hydrogen neutral, resulting in a total atmospheric pressure of 4.6. What is the pressure of the H2 only? So I know I'm going to use Dalton's law of partial pressure. So the total pressure is going to equal to the pressure of the hydrogen, which is what I'm interested in, plus the pressure of the inert argon gas. I know that the total pressure is 4.6. So 4.6 equals P H2 plus 1.4. All you got to do is subtract, and when you subtract it, you get the pressure of the hydrogen gas ends up being 3.4 atmospheres. Okay, now whenever we're talking about measuring pressure, generally pressure is measured with a device called a manometer, a manometer. Okay, what this does, it's usually an open column with some sort of fluid in here. Historically, it was mercury, and because it was mercury, that's where we got the whole idea of pressure being measured in millimeters of mercury. Now mercury's been replaced with things like ethyl alcohol and other chemicals, but it's basically the same idea. You have some sort of tube in here, and the atmospheric pressure pushes down on this liquid, and you can measure the difference in the two columns. The difference in these two columns is represented in millimeters of some sort of fluid. So the difference between these heights actually gives you millimeters of some substance. Now when you know the millimeters of that particular substance and the density of that substance, you can actually figure out what the pressure is going to be. Okay, one of the things that you do need to be familiar with is, and you should be familiar with by now, is STP. STP stands for standard temperature and pressure. The standard temperature is 273 Kelvin, which is 0 degrees Celsius, and the standard pressure is 1 atmosphere, which you can also say is 101,325 pascals, or any of the other units of pressure. But the easiest way to remember it is 1 atmosphere and 273. Okay, so now we need to look at some of the individual gas laws that have come up. The first one is called Avogadro's law, and it was the relationship between the number of moles of a gas and the volume that occupies that gas. Now once again, remember, everything that we're talking about is for an ideal gas. What he found is that if you increase the number of moles of gas and you keep everything else constant, pressure and temperature have to be constants in this case, what he found is that you get a nice straight line graph. So as you increase the number of moles, the volume increases as well. It turns out that whenever you do this, you get a slope, a constant slope, and the slope in this case ends up being 22.4 liters for every 1 mole. And that's where the idea that 22.4 liters is 1 mole of any gas. Now, that doesn't matter if it's H2, O2, or some larger gas, methane. 1 mole of each one of these gases will occupy the same volume. The next law we need to look at is the pressure-volume relationship. It's commonly referred to as Boyle's law, and it just says that as the pressure increases, the volume decreases. So pressure and volume are inversely proportional. So if you have a certain amount of volume, and you can take a look at this, if you have some sort of volume and you were to press down on this, decreasing the volume, the reason why the volume decreases is because the pressure increases. So increasing the pressure results in a decrease in volume. If I were to release this and pressure were to go down, if you decrease the pressure, then you increase the volume. It's a inverse relationship. Now this is discovered by Robert Boyle. He was a contemporary of Newton's. Next we have the volume-temperature relationship. The volume-temperature relationship is known as Charles Law. Not this Charles, but Charles Law. It says the volume of a gas is directly proportional to the temperature. So once again, this is assuming that our pressure is constant and our number of moles are constant. If we keep these two things constant, as you increase the temperature, the amount of volume that a particular gas will occupy will increase at a constant rate. So if you think about this in terms of a hot air balloon, whenever you have your hot air balloon, what you do is you have a fire, and that fire increases the temperature of this gas. As it increases the temperature of this gas, it allows the volume of this balloon to expand. Whenever it expands, you've had a change in volume. That change in volume alters the density of this balloon and causes it to rise. So the whole idea of a hot air balloon is based on this principle of Charles' law, which says that temperature and volume are directly proportional. Okay, Charles' law was actually extrapolated to find absolute zero. So if you were to take any gas and you were to plot its temperature versus volume, it turns out that no matter which gas you used and no matter what circumstances you used, you always had graphs that ended up at the same point. In other words, they would cross at exactly minus 273.15 degrees Celsius. So scientists did some investigating. They're like, well, what's going on? Why are all these gases crossing at the same point? And they determined that that is what we refer to now as absolute zero. Now what absolute zero means is that is the temperature at which Charles' law results in zero volume. So if you were to take a particular gas, any sort of gas sample, and you were to chill it to absolute zero, it would theoretically occupy zero volume. So now we've taken this idea of absolute zero and we've related it to kinetic energy. So now we know that this absolute zero, this point where the occupies zero volume, once again theoretically occupies zero volume, is also the point in which it has zero kinetic energy. So that's why we refer to it as absolute zero. Zero volume, zero kinetic energy. The next we have Gay-Lussac's law, and Gay-Lussac's law is the pressure-temperature relationship, which basically says as you increase the temperature, you increase the pressure. Because, remember, pressure is the number of collisions, the force of those collisions over the surface area. As you increase the temperature, you're increasing the speed at which things hit the walls. So you're increasing the kinetic energy as it strikes the container, and you're increasing the number of collisions. So as a result, pressure increases as well. It is once again a linear relationship. As you double the pressure, or excuse me, as you double the temperature, you double the pressure. What do we do with all these relationships we have? We have a relationship for Avogadro's law, Boyle's law, Charles' law, Gay-Lussac's law. Nobody cares. Okay, you may get a question about whose law was which, but not really. Historically, it doesn't really matter who discovered which relationship, because what you can really do is you can combine all of these things into what we now know as the ideal gas law. The ideal gas law relates all of the individual laws into a single formula. So in order for this to work, the reason why it's called an ideal gas law is because it assumes that kinetic molecular theory is true. And what we now know is this is PIV-NERT. Now PIV-NERT is you have pressure, volume, number of moles, you have a gas constant, and you have temperature. Now the most common version of the gas law constant you have is 0.0821 liter atmospheres per mole Kelvin. Now, just because you have this doesn't mean you can't convert it to other units. Now, the one thing that does have to be constant is the temperature. The temperature must always be in Kelvin. But if you wanted to change this to liter atmospheres per millimoles, you could. If you wanted to change it to Pascal milliliters per millimole. I mean, you could do anything you wanted as far as converting this gas law constant. But if you start with this one, 0.0821 liter atmospheres per mole Kelvin, it'll make your life much, much easier. Now, some of you may be saying, well, wait a second, what about the combined gas law that we learned? Yes, that's true. But what the combined gas law is it's just saying what happens whenever you have a situation in which you have multiple samples. So in other words, I have situation number one, and then I squeeze it, and I have situation number two, and you're trying to relate those two things together. The ideal gas law is used in a single sample situation. So I have this gas at this volume and this pressure and this temperature. How many moles are there? The combined gas law is used for, hey, I have this situation. I did this to it. How is it different? Now, where the combined gas law comes from is once again just a restatement of PIV-NERT. If you were to take PIV-NERT, PV equals nRT, and you were to solve it for N, you'd get N equals PV over RT. Well, no matter what you do, the reason why the combined gas law works is you're assuming that you have the same number of moles. In other words, you have a sealed container. Well, if you have a sealed container and then you squeeze it down, the number of moles is going to be constant. So what you have is number of moles equals number of moles. And so you can say the pressure of the first situation, the volume of the first situation, the temperature of the first situation equals the pressure, volume, and temperature of the second situation. Now you may be asking yourself, well, where did R go? Well, remember, R is a constant. So if R is on both sides, it just cancels out, and you end up with the idea of P1V1 over T1 equals P2V2 over T2. So really just the combined gas law is just a rearrangement of the ideal gas law. So we have our developing level question. This is developing C1. This is a rigid container containing 1.2 atmospheres of xenon is heated from 100 to 500 under isochoric conditions. What is the pressure under the new conditions. So the first thing you should realize is it's under isochoric conditions. What that tells me right there is there's no change in volume. Because there's no change in volume, I'm looking under new conditions. So I have a sample and I have two different situations. So generally what I'm going to look at is I'm going to look at the combined gas law. P1V1 over T1 equals P2V2 over T2. However, since it is isochoric conditions, I know that the change in volume is 0, so the volume is going to be constant on both sides, and that's going to cancel out. Once you have this, you have the simplified relationship here. P1 over T1 equals P2 over T2. Now the next thing you need to do is you need to realize that you can't use Celsius. Remember, these gas law equations require that you be in an absolute scale. So you have to convert these temperatures from 100 degrees to 373, and then 500 you have to convert to 773. Once you do that, you'd plug in. You'd say, okay, it was 1.2 atmospheres, 1.2 over 373 equals the second pressure, which is what I'm looking for, over 773. At this point, you would cross multiply and divide. You get 373 P2 is equal to 1.2 times 773. You would multiply it out and you would solve for P2, and I will leave that for you to do with your calculator, and we'll move on to the next one. The next one is developing C2. It says how many moles of gas occupy the Earth, assuming an average atmospheric temperature of 8 degrees Celsius and a height of 11 kilometers. So this is a little bit trickier. I don't know if this is really a developing level question. It's more of a proficient level question. But the first thing that we need to do is we need to say, okay, we're going to assume that it says an average atmospheric pressure. Okay, the gas or the temperature is going to be 1 atmosphere because 1 atmosphere is what we have for Earth. The next thing I want to do is I want to say, well, I do know the gas law constant, and I know the gas law constant is going to come into play here because it's not saying, hey, you have this much gas and then you do this to it. It's a single sample question. Since it's a single sample question, Pivnerd's going to apply. I also know the temperature is 8 degrees Kelvin, or excuse me, 8 degrees Celsius, which I know is 281 Kelvin. So now, really, in order to find the number of moles, which is what I'm looking for, the last thing that I need to know is I need to know the volume. And this is the tricky part of this particular question. So you have the Earth. That's the actual crust of the Earth. And then you have the atmosphere around it. Okay? It's telling me that I want to know this 11 kilometers from the surface, how many molecules of gas are there. So 11 kilometers from the surface, so I need a sphere that goes around the entire Earth 11 kilometers bigger, and then I need to subtract the actual Earth. Now it doesn't actually seem like it's going to be that much, but whenever you do this, if you know calculus, you can do integrals with it, but you don't have to. So you can do 4/3 pi, and then you can do 6381000, and what that represents is that's the radius of the Earth, okay, plus the 11 kilometers, okay, is converted into meters, minus the original of the Earth. I think I've got too many zeros there. No. And then take that and cube it. And whenever you do this, you actually get an exceptionally large volume, which makes sense. You get something on the order of about 5.62 times 10 to the 18th meters cubed. Now the problem with that is that actually doesn't fit in with the units that we know. So we can't use 5.62 times 10 to the 18th meters cubed. So what we need to do is we need to actually convert this thing into liters, and the conversion factor that we have there is 1 meter cubed is 1,000 liters. And whenever we make that conversion, now we have our volume. I'm going to go ahead and erase all this. We have our volume as being 5.62 times 10 to the 21st liters. Once you're there, this is an easy question. You just plug it into Pivnerd. PV equals nRT, and you would say, okay, pressure is 1, volume is 5.62 times 10 to the 21st. Number of moles is what we're looking for. The rate is 0.0821, and the temperature is 281 K. Take those, rearrange, solve for N, and you should get something on the order of 2.44 times 10 to the 20th moles of gas. You may be thinking that's a really large number for moles, and it is, but remember you were talking about the number of the amount of gas in Earth's atmosphere, so you would expect a large number. The next one says, oops, the next one, let's see if we can get this thing to, there we go. The next one that we have here says 500 mils of water at STP undergoes hydrolysis. What is the volume of gas produced? So the first thing we need to do is we need to be able to figure out that it is at STP. So STP means 22.4 liters per mole. So if I can figure out the number of moles that are produced, I can figure out the number of liters that are there. So the first thing I do is I say I have 500 milliliters of water. When I have 500 milliliters of water, the next thing I can do is I can say for every 1 milliliter, that's 1 gram. That's the density of water. Once I know the density of water, I can say that there's 18 grams of water in 1 mole of water. Okay, and I'm into moles of water. Now, in order to continue on from here, I need a balanced chemical equation. Remember, the balanced chemical equation for the hydrolysis of water is going to be, you're starting with H2O, you're going to H2 plus O2. So I could say I've got to have 2 of these, which makes 2 of these and 1 of these. So if you were to look at this, I can say that for every 2 moles of H2O that I make 3 moles of gas. Now the reason why I can say I make 3 moles of gas is because I make 1 mole of oxygen gas and I make 1 mole of hydrogen, or excuse me, 2 moles of hydrogen gas. So there's 3 total moles of gas. Once you're there, you can use the fact that there is 1 mole, there's 22.4 liters. You would multiply it out just like you would do with any other dimensional analysis question, and when you do this, you end up with the idea that there are 933 liters of gas that are produced by taking 500 mils of water at STP and having it undergo hydrolysis. Talking about the different KMT assumptions, we talked about how worthless it was to refer to the density of a gas. So traditional density is worthless, but we can actually figure out the density of a gas in a much more meaningful way. And how we can do that is we actually can take the idea of PIV-NERD, PV equals nRT. And we can actually make it use this to fit our needs for density of a gas. And here's how we're going to do that. The first thing that we're going to do is we're going to realize that we do have volume here. Okay, so volume is going to be particularly useful for us. If only we had a way to get mass. And the reason why we do have a way to get mass is we have the number of moles. Now remember, the number of moles that you have of something is just equal to the molar mass times the number of moles that you have. That's going to be the way that it equals the mass. So if we can actually rearrange this expression and we can say, well, moles equals mass divided by molar mass, that gives us an expression that we can actually substitute in for the number of moles. So you get the idea that PV is equal to mass, which we're going to use as a lowercase m, divided by the molar mass, which we're going to use as a capital M, RT. Well, now we have the expressions that we really need. We can actually take everything except for m, and we can move it to the other side. And we can take everything, and we're going to take the v, and we're going to move it to the other side. And when we do that, we're going to get P capital M, because we're going to multiply both sides by capital M, divided by RT is equal to M over V, which is our density expression. So we can say density doesn't really depend on mass or volume for a gas. What it actually depends on is the pressure, the molar mass, the gas law constant, and the temperature. So really, what the gas is, the pressure and the temperature will determine the density of that particular gas. There's no need to measure the mass or to measure the volume. Here's an example. It says, what is the density of methane gas? Well, the first thing I know about methane gas is you can say capital M is equal to 16 because methane gas is CH4. Okay, stored under pressure at 8.2 at 50 degrees Celsius. So remember, the first thing you should realize is that you can, of course, have 50 degrees Celsius. Instead, we have to say that it's 323 Kelvin is the temperature. So I have the temperature, I also have the pressure, is 8.2 atmospheres, and I know the gas law constant is 0.0821 liter atmospheres per mole Kelvin. Once you take all those things, you can add them together, or you can plug them in the equation where we have density is equal to PM over RT, or 8.2 times 16. Oh, sorry. This molar mass right here, in order for it to be in units that make sense, it has to be in kilograms. So you're actually going to have to take this thing and, oh no, I'm sorry, it can be in grams. Okay, grams, it's just going to give you grams per liter as your answer, and that's good because we want to deal with grams anyway. So 16 grams divided by, you're going to have 0.0821, which is the gas law constant, and you're going to have 323, which is the temperature on the bottom. When you multiply this all out, you end up with something of about 4.94 grams per liter, which is a very, very, very low density, which makes sense when we're talking about the density of a gas. So now we need to talk about the difference between effusion and diffusion. Effusion is the rate at which gas escapes from a small opening. So if you poke a little hole in a container, it's how fast can the gas get through. Now, whenever you were talking about diffusion, diffusion is like where you have a much larger opening and just saying, hey, what's the rate at which they kind of equilibrate? So whenever they equilibrate, that's diffusion. Whenever you have some sort of tiny hole that's allowing gas to seep through, that's what we call effusion. Now, one of the things that affects effusion is the kinetic energy. This is known as Graham's law. It just says that the kinetic energies are equal. So whenever you're comparing this rate of effusion, this obviously assumes that they're the same temperature. Okay, the temperature of, or how fast one gas effuses versus how fast another gas effuses, they're the same temperature, so they're going to have the same kinetic energy. Now, where this is particularly useful is if you have a mixture of gases, and you have some small gases and some large gases, and you want to separate them. Well, they will effuse at different rates, which means they'll pass through a tiny opening at much different rates. And the rates can actually be figured out this way. You can compare them. You can't say with absolute certainty, oh, this many moles will come out per second. But instead, you can compare the rates of effusion. Now, the rate of effusion is just basically equal to the molar mass, but it's an inverse one. So if you were to look at the rate of gas 1 escaping divided by the rate of gas 2 escaping, it's equal to the molar mass of 2 divided by the molar mass of 1. The reason why is the kinetic energies are the same, things are going to cancel out, and so that's what it ends up being. So we have this idea of developing, you have a 3-liter sample of helium, which was placed in a container fitted with a porous membrane. Half of the helium effused in 24 hours. So half effused in 24 hours. A 3-liter sample of oxygen was placed in an identical container. How long will it take half the oxygen to effuse through the container? So we can say is rate of 1 divided by rate of 2 is going to equal to the molar mass of 2 divided by the molar mass of 1. So if we can say that the rate this thing took was 24 hours, so we can say 24 hours up top is how long it took for the first one, and then the molar mass, I'm trying to figure out what rate 2 is. Molar mass 2, in this case, oxygen is going to be 32. The reason why it's going to be 32 is oxygen is a diatomic divided by helium, which is 4. So if you look at this, you can actually solve for the rate. Whenever you do this, you end up with a value of about 2.8 times longer, or about 68 hours is what it ends up being. Oh, that's why. This right here is supposed to be the square root, okay? So it's supposed to be the square root of the masses, not the square root of the rates, but the square root of the masses, because of the whole idea of kinetic energy in the 1/2 mv squared. I can go over that in class again. Okay, next we have KMT assumptions revisited. So the first assumption that we made was that gases are very small molecules. That is, for the most part, true. It's not always true because gases can be compressed. Whenever you take this thing and squeeze this thing down so it only occupies this much space, but all of these molecules are in here, now all of a sudden the volume of the gas itself takes up a lot of space. So this assumption is only true when you have a very, very low pressure. Whenever there aren't very many molecules hitting the sides, then you can say, okay, this is a true statement. The second assumption we made is that molecules are in constant random motion. Well, that's not always true. Okay, motion is not random, but instead depends on the sum of the forces. So are there partial positive charges? Are there partial negative charges? Are they attracting each other? Those sorts of things. So when it is true, the reason why it is true is when you have high temperatures. Whenever you have high temperatures and this thing is moving at, 100,000 meters per second, well, that's ridiculous. Let's say 1,000 meters per second. The fact that this thing comes somewhat close to it is barely going to affect the motion of this at all. In addition to that, by having a high temperature, it's going to be in a constant motion. Okay, when this isn't true is whenever you have very, very low temperatures. So now, whenever you have this positive and this negative moving kind of slowly by one another, they're more likely to change direction, and they go like this and move towards each other. Okay, so that's the assumptions of KMT number 2. The third one says collisions are numerous and elastic. Okay, now atoms can collide and stick together. That's what we call a chemical reaction. So this is not always necessarily true. And in fact, elastic collisions with a container or elastic collisions are very, very unlikely to occur. Okay, it is very difficult to have 100% transfer of kinetic energy. So it's not likely to occur. Now it does generally happen when molecules are inert, and it's close enough where we can make this assumption and say that it's pretty much the case. KMT assumption number 4, there are no intermolecular forces. Come on, that's ridiculous. You know about intermolecular forces now. It's all we talk about is intermolecular forces. So now when this assumption is true is when there's low pressure. Whenever there's low pressure, there's no collisions with molecules. So a large volume, low pressure situation, low temperature situation, high temperature situation is one in which the intermolecular forces play less of a role. The fifth one says that the kinetic energy of molecules is proportional to temperature. Molecules near 0K have moving electrons, so technically still they have kinetic energy. So at very, very low temperatures, this one gets to be kind of tricky. But for most normal temperatures, and obviously for high temperatures, it is true. So now the question is this: what happens when we take these assumptions and throw them out the window? What we do is we get something called real gases. All gases can be confined as real gases. So it's one of those whole ideas that all gases are real, okay, but some can be assumed to be ideal. And ideal are a smaller subset. Now, real gases do not have the assumptions of ideal gases. So we have to correct the idea of the ideal gas law. So the ideal gas law was Pivnert, PV equals nRT. So we can actually take this same equation and we can modify it for real gases. And that's what you get when you get this. This is what's called the van der Waals equation. You get P plus n squared A over V squared times V minus NB times equals nRT. So basically, this is the exact same equation. The only new factors that you have here is this A term and this B term. And what those are is those correct for intermolecular attractions, which is the A term, and they correct for volume, which is the B term. So now you can actually calculate these from constants. We're not actually going to do that. If I ever ask you to do a question with these, A and B will be provided in a table. So it'll say, hey, here's A and B. Tell me what these are for this particular situation. Okay, the last... So this is what we see. When you have them in a table right here, you have your A and B. Now it says, what is the difference in volume for 1.5 moles of xenon occupying 100 atmospheres at 100 K according to the real and ideal equations? I'm going to save this one for class because this one can be a little tricky as far as using the table and looking at both the ideal and the real gases. So make sure that we go over this one in class. So now we have to revisit the idea about solubility. Gas solubility is a little bit different. It generally follows the same rule as polar and nonpolar substances. So generally speaking, polar gases will dissolve better in a polar solvent, but generally speaking, you can get just about any gas into any solution just by kind of bubbling it through. That's why you see carbon dioxide bubbled into water, and that's what we call carbonated water. The general rule is the solubility of a gas will actually decrease as the temperature increases. Now that's the exact opposite of what you have for a solid. And the reason why is as you give a gas additional energy by increasing the temperature, you're actually increasing the energy of the molecule and making it more likely that it will fly out of the solution. The last thing that we need to talk about is K expressions with gases. This is actually going to come up in the second semester, so we want to go ahead and address it now. The first thing is, this is the whole idea that we have of the hydrolysis of water. Whenever we write a K expression, we generally do it as H2 and O like that. But the problem is these right here are not solutions. Whenever we express something in brackets, it's because it's in a molarity. Now we can't do that, so instead what we do is we put the brackets and then we put a P. The P stands for pressure, and then we put the substance right underneath it as a subscript. So you see pH2, which is the pressure of the hydrogen gas. That's still squared. Then you have the P, which is the pressure of the oxygen gas. Now, one of the most important things about this is the K expressions require that the pressure be in atmospheres. And that's actually why we use the R value in liter atmospheres per mole Kelvin, even though it makes more sense to use it in something like kilopascals whenever we're talking about units. The reason why is the math actually works better proportionately whenever you look at the K expressions this way. So it's more important that you actually put them in atmospheres whenever you're looking at K expressions.